So hello students. So today I am with the new experiment of RC coupled amplifier. So basically we are going to form a single stage common emitter RC coupled amplifier. Okay. So the main purpose of this circuit is basically pre-amplification, so that we could amplify the weak signals. Okay. So that it could be used for further amplification and circuit use. So in the common emitter amplifier case, output is 180-degree phase shifted with respect to input signal. Okay. As we already know that region between the cutoff and the saturation is known as active region. So the region where the bipolar transistor operation is completely switched off, that is known as cutoff region, and the region where the transistor is completely switched on, that is known as saturation region. So we are going to use actually the transistor here. Okay, for this amplification. Okay, so here I have written that how the circuit works, and here is my circuit. Okay, so I will explain you the circuit diagram. Okay, so this is the function generator from which we are going to give a small AC signal here. So these two, this C2 and C3, are the coupling capacitor here, this R5 and the R1. Okay, these are voltage divider biasing resistors. So these are basically used so that it could give a better voltage here to the base of this transistor. Okay, and this coupling capacitor, the C2, is used so that there should not be any DC part here. Okay, in this base. Okay, as we already know that the capacitor is used for removing the DC voltage here. Okay, it allows only AC here. Okay, so these two resistor R2 and R3. So we are going to use this R2 and R3 as the common emitter biasing resistor. So basically these resistors are used in such a way that they should drop this VCC, okay, by around 50%, okay, for this given circuit. Okay, this emitter capacitor C1, okay, and this R3, it is used for making a negative feedback. So since we are going to make a negative feedback here, so it will make our circuit operation more stable. Okay, and for proper biasing, as already I have told, this R1 and R5 resistor are used so that we could give proper biasing to our base of this transistor. Okay, and after this coupling capacitor, we will get our output. Okay, so this is basically the circuit. Okay, this one is the frequency response of the waveform here. Okay, so in this uh, experiment we are going to find out that what are the input voltages. Okay, when we are going to provide the input frequency, we could provide two to three different types of frequency here, but we will limit our input voltage to a very lower part only. Okay, as the voltage gain would be very high here. Okay, so we will take the observation, okay, by the help of our multisim experiment. Okay, and we will also provide, sorry, not provide, we will also make this frequency response graph. So now just move on to the multisim. So here is the circuit diagram here, and here you could see that I have given here frequency of 1 kilohertz and amplitude is 25 millivolt peak to peak. Okay, so here we are going to get the output here at this part. So this violet line is for the input signal only, okay, and this red color line, it will give us the output of this amplification. Okay, so just to run this simulation and take the output. So we can look the output here. Just stop the simulation. So you could look here. This violet one is the input and this red one is the output signal. Okay, so just check the peak to peak value of both the input and output. As we already know that input we have provided 25 millivolt peak to peak, so it will come to be 25 millivolt peak to peak only. So just check here the difference between both the cursor. Okay, so this thing is present in channel B here. So in the channel B, just see here 49.79 millivolt peak to peak value has been present here. Okay, and here for the output you will see, for the output we are getting the value of around 8.715 volt. Okay, so while given amplitude of 25 millivolt peak to peak, we are getting this much of amplification. Okay, so our input voltage is 49.74 millivolt from peak to peak, from the highest portion to the lowest part, and we are getting 8.715 volt of peak to peak value of this output voltage. Okay, so you could just write this thing in here. Okay, the output voltage we are getting 8.715, so we will write here 8.715. Okay, and the input voltage, as we already have given, 25 millivolt. Okay, so sorry, it was around 50. Okay, the amplitude is here 25 millivolt peak to peak. Okay, but the peak to peak value which we are getting, it is 49. Okay, so here basically we are going to just divide it, this thing, 8.715 volt to 50 millivolt peak to peak. So if you will do the calculation, I will just open the calculator here. Okay, so 8.715 volt, so just convert it into millivolt here. So it should be 8715. Okay, this much millivolt of output voltage we are getting. So I will divide it by 50 millivolt peak to peak, and then we are getting around gain of 174.3. Okay, so we are getting 174.3. Okay, this is the voltage gain which we are getting through the circuit. Okay, similarly you could find it, that thing, in decibel also by the formula 20 log V output by V input. Okay, so just change the frequency 2 to 3 times and just check the value. Okay, what the value you are getting, and afterwards in the observation you have to check one more thing also. I will just write here, you have to find out the bandwidth. Okay, so the bandwidth of the signal, sorry, this one is small. So the bandwidth you will find by the help of this thing. You will have to just check the difference between this F1 and F2. Okay, so F1 and F2, how we will get? We have to find out this thing in multisim only. Okay, so I will show you that how to perform this part here. So this thing I have done. Okay, so I will close this thing. Now just in the interactive, I will just choose AC sweep. Okay, and we have to change the frequency. Okay, as the frequency will change, we will take the graph in the decibel. So vertical scale would be decibel only. Okay, so input starting frequency is 1 hertz and the stop frequency is 10 gigahertz. So you could change the value of these things here, but let it to be 10 gigahertz. Sweep type is decade only. Okay, and number of points per decade we are going to use 10. Okay, so now in the output part, I have chosen here V6, as the V6 is the output provided by this thing. If you want, you could see this. The name of this thing is 6. Okay, the sixth one, this is the sixth arm. Okay, so when you will provide the data here, V6, it will take the variable V6 to be the output part. Okay, it will, this AC strip will change the frequency, input frequency, and it will provide us the different value of voltages here. Okay, the gain, and since I have used here decibel, so it will provide us decibel gains. Okay, gain in decibel. Okay, so just run this thing. So basically this one is the phase degree graph, so we don't need this thing. So I will just right click and delete this graph. Okay, so basically this one is the AC sweep graph of amplifier. Here is the magnitude and here is the frequency. Okay, so just amplify this thing. Okay, so in this thing, since the background is black, so just make it white. Okay, now you could use the grid lines here. Okay, and we will use the cursor to find out the values. Okay, the values for which we should get the data of bandwidth. Okay, as we already know that for the finding the bandwidth we need to find the f1 and f2. So for f1 we have to find out that part of this gain for which the gain is less 3 dB from the highest part. Okay, that means from the highest gain we have to subtract 3 dB. Okay, and the point where this part matches, that would be our f1 frequency. Okay, this f1 would be found out in the x-axis, and this f2 would be also find out in the x-axis, but we have to find out the y coordinate, okay, such that the gain at this point would be less 3 dB than the highest point. Okay, I will show you that how to do that thing here. Okay, so these one are the two cursors here. So just look here, I will make both the cursor at the same part. Okay, just look here, the x1 and y1, these are the coordinates of this first cursor where it meets with the graph. So this is the coordinate of this point. Okay, and here the x2 and y2, basically this is the coordinate of this point where the second cursor meets the graph. Okay, and the dx is the distance between both the cursor in x direction. Okay, so basically here we are seeing that the gain of y1 or y2 both are 13.4743. So basically we are getting the gain of around 13.4743, and we do need to find the point where the value of y should be 3 less than this maximum gain. Okay, so 3 less than 13.4743 is 10.4743. Okay, so I will just move the cursor to that part, or I could just directly feed the value here. Okay, so just right click on this thing and set the y value. Okay, so just see here we are seeing two type of set y value. So this one is showing this right arrow, and this one is showing this left arrow. So we are going to place this cursor on the left hand side here. So we will choose this part, and I will just write here the value of 10.4743. It was 4743. Okay, it will automatically move to that part. Okay, so this is the thing here, and similarly we will just make this cursor to the y value here, so that it should be also 10.4743 here. Okay, so just see here both the cursor are at f1 and f2 frequency. Okay, as the gain here is less 3 dB than the maximum gain. Okay, so now we have to find out the difference between the frequency of these two parts. Okay, so we will find out the coordinate of this line. Okay, so here we are seeing that the x1, okay, the x1 is the this coordinate. Okay, the x1 and y1 are the coordinate of this point, so that means the x1 is also the coordinate of this point. Okay, so x1 is 96.5993. So we have found out that the f1, our this f1 part is 96.99, sorry, 96.5993. Similarly, the x2 coordinate here is 12.0019 megahertz. Okay, so the coordinate of x1 and x2 we have found out. The x1 coordinate is 96.5593. This one is f1, and this x2 is 12.0019 megahertz. So this one is this part, and x2 minus x1 we have already got as dx. It is 12.0018 m, that is megahertz. Okay, so we can simply write here the bandwidth is equal to f2 minus f1. Okay, and from this thing you can already see that the f2 is our 12.0019 megahertz, and this x1 is 96.5993 hertz. Okay, so by the help of this graph we have found out that what is the bandwidth for this gain. Understood? And if you want you could import these data in excel also by the help of this button. Click on this button and just click on this. Okay, all the data would be given in the excel now. Okay, it will import all the data to the excel. So just see here, so this one is the excel data. Okay, so this y is the magnitude. Okay, it is in decibel, so you could write in here gain. Okay, gain in decibel you could write, and here you could write frequency. Okay, so this one is the frequency and this one is the gain. Okay, so you could see here these all are data. So you could make the graph here also in the excel. Okay, or you could just import the graph from here also. Okay, So by the help of this graph, we have found out that what is our bandwidth, okay, and what is the frequency F1 and frequency F2, okay. So these data would be filled here. So I hope you have understood that how to use this RC coupled first stage amplifier, okay, to find out the gain and to find out the bandwidth, okay, to find out the frequency response. So basically this is the frequency response of this thing, okay. So this experiment is over. This was the final part of this